Hey everybody, and welcome back to Patel Academy. Today I wanted to talk about a very important topic in calculus, sequences and series. Now because of how broad this topic is, I decided to split it up into two different videos. So for this first video, I'll be talking about the convergence of sequences and series. Now specifically, I wanted to talk about the definition of sequences and series as well as some properties associated with them, then talk about the major convergence tests, and then finally end off with ways to estimate the value of an infinite series using partial sums. So let's get right into it. What exactly is a sequence? Well, in middle school or in high school, you may have seen a set of ordered numbers written something like this: 1, 2, 3, or maybe a set like this: 1, 4, 9. And essentially these are sequences. It's just a list of ordered numbers. So I'll write that down here. It's a set of ordered numbers. And so what's interesting about sequences is that oftentimes you can get the general term of the sequence, which is really helpful in identifying whichever term you want, or perhaps how the end value of it, or the convergence point, which I'll talk about in a little bit. So for example, for the second sequence, I can write this as a function of n, where n is the term number. So in this case, f at n is equal to n squared. And these can be varying, they can be rational, they can be polynomial, but the point is that just these random numbers can often be expressed as a function. And so regarding this definition, there's a couple of key terminology that you should know regarding sequences. The first one being what a monotonic sequence means. So monotonic essentially means that the sequence is increasing or decreasing. Similar to what a monotonic function is. And so increasing or decreasing can be over the entire function, over the entire sequence, or within certain aspects of it. But the point is that it should generally observe a single trend. And so we'll see later on in the tests that oftentimes a sequence, when plotted, will model something like that. And so it's the idea that as n gets larger and larger, the function is decreasing. So this still would classify it as a monotonic sequence. Now, some other key terminology points include the idea of convergence and divergence, perhaps one of the most important things across this entire unit. So what does it mean to be convergent? Well, as you may have heard in other contexts, two things converging means they meet at the same point. Specifically, they meet at a point. And so that's what convergent really means, is that the sequence over time will reach a single point. Or in mathematical notation, the limit as the terms go to infinity of the sequence is a constant value L. A lot of times this will be 0 or 1. And so an example of this that I can give is the sequence 1, 1/2, 1/3, 1/4, etc. Classified as 1 over n, the sequence will converge to 0 over time. However, this is important that a lot of times, as I'll say in series, the sequence can be convergent, but the series itself might not be. So in this particular case, the series of the sequence is not convergent, and we'll explain why. Now, what's the opposite of convergence? Well, it's divergence. And so that's essentially the exact opposite. There is no finite number that can describe what the series will go to. And so you can say that the series will go to plus or minus infinity, or we can say that the limit does not exist. And so an example of this is your classic 1, 2, 3, 4. As n goes to infinity, the term will also go to infinity, so it technically doesn't exist. There's no single point that the sequence will converge towards. Now finally, the last terminology piece is about bounding. Now oftentimes, regarding functions, we talk about restrictions. That's essentially what happens. It's like restrictions on the sequence. And so you can be bounded above, below, or both above and below. And so if you say that the sequence is bounded above, that means that your sequence is always going to be less than or equal to some value. I'm going to call it L2. If it's bounded below, that means that your sequence is always going to be greater than or equal to some value L1. And if it's both, that means that there exists L1 and L2 that bound the sequence on both sides. So both of the above things are true if it's bounded both above and below. And we can call that absolute bounding. Now, in terms of some properties of sequences, I'll specifically be talking about limits of sequences. Now, as I said earlier, sequences can often be modeled by a function. So think about it as if you were taking the limit of f at x. I'm going to say as n approaches some value a. Well, let's say if I have two sequences now, f at x and g at x, right? Plus or minus. Well, we know that we can split the limit up. So it's as n approaches a of f at x plus or minus the limit as n approaches a of g at x. Now the same thing applies for addition, as shown above, subtraction, multiplication, and division. Another limit property that still applies here is if you're taking the exponent. So if it's, let's say, the limit of f at x all squared, and that's equal to the limit of f at x, evaluate that first, and then square that limit. And the squeeze theorem also applies here. So just a recap of the squeeze theorem, let's say if I have some sequence a at n, which is always less than or equal to a sequence c at n, which is always less than or equal to a sequence b at n. And if the limits of a at n and b at n are always L, they're both L at a point, that means that the limit of c at n is also going to be equal to L. And that's the squeeze theorem. Write that down. Squeeze theorem. And so each of these limit properties still applies to sequences, and as we'll see, they'll still apply in part to series. And so that's essential because a lot of the stuff that we're going to be covering in terms of this topic are going to revolve around the idea of taking the limit and identifying what the final limit is and making inferences based on that final value, L. Alright, so now talking about series. Well, what exactly is series? You may have seen this sign, the sigma sign, before. This represents sum. And this also is what we use to denote a series. So essentially what a series is it's the sum of a sequence. And so you can have partial sums or infinite sums. So partial sum would be something like n is equal to 1 from n is equal to 1 to 5 of n squared, for example. You'd evaluate that for n going from 1 to 5. That's a partial sum, and we would call that the sum as 5. However, you can also have infinite sum. So this is where you'd have the sum n goes from 1 to infinity of that same thing, n squared, for example. And we call that just the general Sn, or even just S, for the sum of the entire infinite series. And so in terms of some terminology, similar to sequences, we have the idea of converging versus diverging. And so the definition remains the exact same. Converging means that the series, not the sequence now, but the series value approaches a certain point, while diverging means that the series value will just extend to positive or negative infinity, or you can't actually figure it out over time. So like an oscillating series, for example, where it's -1, +1, -1, +1, -1, that won't ever actually converge to a point. It'll just keep oscillating around 0. So that's also considered divergent. In terms of some properties now, these properties, especially the second one that I'll cover, are going to be very important. So the first one is scalar multiplication. So if I have the series of some sequence a at n, and if I say that this is convergent, then the series c times a at n is also convergent. And it's actually equal to c times the original series, as long as c is a constant. And think about how this makes sense. In this new series, c times a at n, each term is multiplied by c. But at the end, you can just factor a c out of every single term and get the original sequence a at n. And so that's why you can just pull the constant out. And it doesn't affect convergence. Similarly, what's interesting is that oftentimes, let's say if I have a sequence as a function of x. So let's say if I have the sequence as n goes to 1 of infinity of x to the n plus 1. This is known as a power series, and I'll cover this in more detail in my second video. But I can rewrite this as x times the series from n equals 1 to infinity of x to the nth, and this won't affect convergence because the term I brought out was independent of the variable in the series. In this case, the variable is where the index is, so n, because that's the number that's increasing. Because this x I pulled out is independent of that n, it won't affect convergence. Now the second property is called index shift. And while this can oftentimes seem intuitive, it's important to know exactly how this works in case of a more complicated series comes up that you need to transform in order to use a certain test. So let's say if I have the sum as n goes from 2 to infinity of x to the n plus 3. But I'm going to use a test that, for example, requires the bottom index to be n is equal to 0. What I can do is use an index shift. So I'm going to say let I equal n minus 2. So that at the starting point when n is equal to 2, I becomes 0. And then what I know is that n is equal to I plus 2, right? So what I can do is I can rewrite this sum as at n is equal to 2, this becomes I is equal to 0. At infinity, this will stay infinity. But then I get x times I plus 2. This is my substitution for n. And then plus 3, which is the sum from I is equal to 0 to infinity of x to the I plus 5. Now, while this may seem intuitive for many of the cases, it's important for you to know exactly how this works, because sometimes you can get lost with really large series, like if there's 5 different terms within the series, or if you start getting derivatives within the series, which we will see later. It's important to know the fundamentals of how the index shift works. And then, similar to sequences, along with multiplication, you can, if you have 2 series being added together, you can just add the inside terms and take the overall series. So the series of a at n plus b at n is equal to the series of a at n plus or minus the series of b at n. In this case, though, multiplication does not work. So you can't have the series of a at n times the series of b at n is the series of a at n times b at n. That doesn't work. Okay, so now we're going to move on to convergence tests, which is arguably one of the most important topics within sequences and series because it'll directly tie into all of the later content that we do as well. So in terms of convergence tests, there's 9 different categories and 10 tests. I'll go through each one, but for the most important ones, I'll indicate whether you should know this for sure or not. So the first is called the Nth Term Test. The Nth Term Test. Now, what is this suggesting? Well, think about what the definition of convergence is. Well, the convergence says that the series has to approach a certain value over time. But because it's a series, right, the inside function has to approach 0 over time for the series to stop growing infinitely. And so essentially what the nth term test says is that we take the limit as n goes to infinity of a at n. Oh, by the way, convention for a series is you take the series of something a at n. So if I ever refer to a at n, that means I'm referring to the inside. So the actual function that the series is being taken of. So we're taking the limit as n goes to infinity of a at n. And if it's equal to 0, and this is where wording becomes really important, because it may or may not converge. Oops. But if it's not equal to 0, it will diverge, guaranteed. And so what's interesting about this test is that oftentimes you never really use this to show convergence, pure convergence. You always use it indirectly to show divergence. And so why is this important? Well, a lot of times with polynomial functions, for example, you know that if you have something like x to the nth plus 3x to the n minus 1, for example. Well, because this is polynomial, generally polynomials, its end behavior is extending to negative or to positive infinity. And so we know that over time, a function of this model will diverge. And the idea of showing that it'll diverge is by taking the limit as n goes to infinity. And so you usually use this test with rational or with polynomial functions to immediately show that it'll diverge. And a lot of times in multiple choice for AP, it's a quick way to get an answer, because oftentimes you'll have like different values, or you'll have different answer choices that seem really similar, and then you'll have one that just says diverge. And so if you can isolate that it diverges really easily, you'll save yourself a lot of time. So let's do an example. So we have the sum as n is equal to 5 to infinity, so n going from 5 to infinity, of 6 plus 8n plus 9n squared over 3 plus 2n plus n squared. Alright, so first, it always helps to define what a at n is equal to. So in this case, it's 6 plus 8n plus 9n squared over 3 plus 2n plus n squared. And so now we're going to take the limit as n goes to infinity of a at n. And so what do we know about taking the limit as n goes to infinity? Well, it's all about dominance, right? Or you can also use the idea that both the top and the bottom have the same degree, so you can just compare the coefficients. Or you can consider dominance. And so in the numerator, the n squared term is going to be growing the most rapid. So as n goes to infinity, we can assume that this function turns into just n squared on the top, so 9n squared, on the top, and on the bottom it would just turn into n squared. So the limit is 9. So what do we know now? Because 9 is not equal to 0, obviously, we can say that this series diverges. And so the proper way to write that is that the series, you can choose to restate it if you want, it's not necessary, diverges by the nth term test. And by the way, sorry for all of the pop-ups that are coming up, that's just PowerPoint. So that would be the statement. The series diverges by the nth term test, and if you wanted to provide further justification, you can say because the limit is not equal to 0, suggesting divergence within the series. So that is the nth term test. Now moving on to the second convergence test, which is geometric series. Now what is a geometric series? Well, you may have explored this in a little bit of detail before. A geometric series is something of the form, a to the nth. It's the sum of an initial value a times a common ratio r to the power of n, where n is constantly increasing. And in general, our index starts from n is equal to 0 to infinity. But sometimes, because a lot of the series we'll start with n is equal to 1. We can modify this a little bit by saying that it's a times r to the power of n minus 1. These are identical. You can verify that using an index shift. And so, an example of this, one of the most common ones, is 1 plus x squared plus x cubed dot dot. And so what this means is that our a value is equal to 1, our r is equal to x, and as you can see, x is at the power of 0 on the first term, then 1, then 2, then 3, dot dot dot. And so now we talk about the actual test. Well, if you can get your series or your sequence, your series, into this form, a times r to the nth, or a times r to the n minus 1, then the test says that if the absolute value of r is less than 1, then the series converges to a over 1 minus r. So this is a formula that you're going to need to know. However, if the absolute value of r is greater than 1, the series will diverge. And so this is an example where there's an absolute statement. It either diverges or it converges, and it converges to a certain value. This we won't see in many of the things converging to a certain value, but at least this provides it will converge or it won't converge. So let's do an example. We have the sum as n is equal to 1 of infinity, as n goes from 1 to infinity, of negative 6 to the 3 minus n over 8 to the 2 minus n. Alright, so what do we know about geometric series that start with 1? Well, the general formula that we want is n is equal to 1 to infinity of a times r to the n minus 1. So this one involves a little bit of algebraic manipulation. So first, I'm going to say a at n is equal to negative 6 to the power of 3 minus n over 8 to the power of 2 minus n. Now remember that I can factor out a negative from the exponent, right? So I'm going to get negative 6 times negative n minus 3 over 8 times negative n minus 2. And when we have a negative on the top and bottom, we can just flip it. So this becomes 8 to the power of n minus 2 over negative 6 to the power of n minus 3. Okay, now that we have this, what we realize is that we want to get n minus 1. So what exactly does this mean? Well, on the top, this is n minus 1 and then minus 1, right? N minus 2 is n minus 1, what we want, minus 1. So we can split this up as 8 to the power of n minus 1 times 8 to the power of negative 1. This would result in the same equivalent expression, 8 to the power of n minus 2. And then over negative 6 to the power of n minus 1. And then what's left? Well, you need a negative 2. So I get negative 6 to the power of negative 2. And so now you can kind of see how this becomes a geometric sequence. Our a value then becomes, well, this is 1 over 8 divided by 1 over 36, and then times negative 6 over 8 to the power of n minus 1. And so now what do we notice? So now we use the geometric series test. I'm going to write GST, not tax. GST, and then I'm going to say that the absolute value of r is equal to the absolute value of negative 6 over 8. This is our common ratio, which is equal to 6 over 8, and 6 over 8 is less than 1. So this suggests that the series will converge. And just as an exercise, what does it converge to? Well, it'll converge to a over 1 minus r. So 36 over 8 divided by 1 plus 6 over 8, whatever that turns out to be. I believe it'll actually be 36 over 14 or 18 over 7. And so that's an example of how you can use the geometric series test in order to identify if it'll converge and what it'll converge to. And unlike the last example, I didn't write out the series will converge by the geometric series test as the ratio, the absolute value of the ratio is less than 1, but on the AP exam you probably should, to make sure that you get full points. Okay, the third test. The third test is that I've decided to include here is the harmonic series / the p-series test. And so what is the harmonic series, first of all? The harmonic series, which is arguably one of the most important series you should know, is anything of the form c over n, where c is a constant. Sorry, this should be sum of c over n. Oh boy. And so this includes things like the sum of 1 over n, which is the most famous, sum of 3 over n, for example, dot, dot, dot. And each of these have been proven to diverge. This can be shown through the next test that I'll cover, which is the integral test right after this. But for this first test, you just have to assume that harmonic series will always diverge, and this will always be true regardless of what that constant is. Now, different types, not necessarily different types of harmonic series, but different types of these reciprocalized series are called p-series. And these are of the form the sum of 1 over n to the power of p. And so what does the p-series test say? Well, if p is greater than 1, the series will converge. If p is less than or equal to 1, 1 being this harmonic series case, this will diverge. Okay, seems fairly straightforward. I'm not going to show the entire proof of this in this video, but you can use the integral test, which I'll explain in a minute, in order to figure out exactly why this p-series test works. So it's essentially just a simplification. So an example. This is very straightforward. We have the series as n goes from 1 to infinity of 1 over n pi. First, we identify that this is a p-series, and that because pi is greater than 1, this will converge. Okay, fairly straightforward. The next one is the integral test. This one is one that requires a little bit more proofing because it has a couple of more conditions. So we need a sequence. Oops, sorry. A at n equals, I'm going to write it this time as a function. Function of n, function of x, whatever. We require it to be continuous, positive, and decreasing. These are very important conditions. Usually, you would need to prove all of these. Some of these, though, will be a little bit more intuitive. The decreasing one is the main. So I'll talk about that for a second. How do we prove that something is decreasing? Well, you'll be given a function. What does it mean for a function to be decreasing? Well, its derivative has to be negative. So what you have to do is you have to find f prime at x and show f prime at x is less than 0 for large values of n. So once again, this goes back to when I talk about sequence. A lot of times what you'll see is a function will do something like this. For a little bit of n, it'll be decreasing, and then long term it'll be decreasing. This is fine. It's just for large n that you need to make sure that it's decreasing. So then what is the integral test? The integral test states that if you have a function that follows these things, and then if you have the sum from n is equal to some value k to infinity, most of the time this k will be 1, but it can be other values like 2 or 3, that's fine, of this a at n, then you take the integral from k to infinity of a at n. Now usually a at n will be expressed as f at x, so I'm going to write dx here, but you could fill in that a at n as f at x, and then it'd be an actual integral. And then you evaluate this. And so you figure out, using improper integrals, if the integral converges, then the series converges. But if the integral diverges, then the series will diverge. Alright, so that's fairly straightforward. Usually the hard part with the integral test is figuring out when should I use it. Because a lot of times some other tests might seem appealing. Most of the time with the natural log function, you would be using the integral test. Or sometimes with functions like e to the x, for example, something related to that, you'd be using the integral test. And if you ever forget the p-series test, then you can use the integral test and you'll still get the correct convergence or divergence, because the p-series is based on this test. Alright, so an example. Well, I see n squared over n cubed plus 1. Now, based on the test that we've learned so far, it's not a p-series and it doesn't look like a geometric series, and the nth term won't really help us in this case. Even though it is irrational with polynomial numerator and denominator, if I take the limit as n goes to infinity, I'll get 0 for this, which doesn't suggest that it converges. It's inconclusive. It just shows it doesn't diverge. So, what can we do? Well, we can use the integral test. And so, I'll define my a at n, or my f at n, to be n squared, over n cubed plus 1. And I know that my k value here is 0 because it's n equals 0. So I'll take the integral from 0 to infinity of n squared over n cubed plus 1. In this case, everything is in terms of n, so I do dn. And so what do I get? Well, I'll just use a simple u substitution. So u is equal to n cubed plus 1. So du is equal to 3n squared. And so, this is 0 over here. So then I get, this is the integral from 0 to infinity of 1 over u. And then this entire thing is, because of this 3n squared, this is being multiplied by 1/3. So my integral evaluates to 1/3 ln of the absolute value of u, and this is evaluated from 0 to infinity. And so what do we figure out? Well, when we plug in infinity into this, this is the ln function. The ln function will go indefinitely. So this would be infinity minus, what's the ln of 0? Well, I mean, ln of 0 is also undefined. So this is, we can just say that this does not exist. It's either indeterminate or it's infinity minus infinity, which doesn't exist. And so what do we get then? Well, because the integral doesn't exist, we can also say it's divergent. And so that means that the series is divergent. Once again, by the integral test. Alright, we're making pretty good time. The next one that I wanted to talk about was a special kind of series that doesn't usually come up, but when it does come up, it can be really tricky if you haven't seen it before. It's the telescoping series. So what is a telescoping series? So a telescoping series is a series in which terms often cancel out with it. So you'll have something like maybe 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, dot, dot. And so each of these terms will cancel, and so you'll be left with just the first and the last, or some combination of terms. And so because you'll only be left with a couple of terms, you can then evaluate the limit of the last term and keep these first constant terms. So for example, in this case, let's say if my series was 1 over n minus 1 over n plus 1. This is the sum. As n goes from 1 to infinity. Then think about what my terms are going to be. This is a minus, sorry. It becomes 1 minus 1/2 plus 1/2 minus 1/3, exactly as the above sequence. And so what will I be left with after all of these cancel? Well, I'll have 1, and then I'll have this last term, 1 over n plus 1, and the n will be infinity. So I'll just take the limit as it goes to infinity, as n goes to infinity of this entire thing, and I'll get 1. So this telescoping series will actually converge at 1, because everything else will cancel out or will become 0 as n goes to infinity. And so this isn't really like a test per se, but it's an example of a series where you kind of have to use your knowledge of limits, and so they consider it like a special type of test. So let's try an example. This is the sum as n goes from 4 to infinity of 10 over n squared minus 4n plus 3. Now, at first glance, this may not look like a telescoping series, and you may be tempted to try and integrate this, maybe use partial fractions and integrate it. But the easier way is to use partial fractions, yes, but then to just identify it as a telescoping series. So let's think about this. 10 over n squared minus 4n plus 3. I'm going to break it up into its factors, so this is going to be n minus 3, and then n minus 1. I'm going to have a and b on top. And so you can set up the system of equations, or you can use the shortcut, which is the cover-up method. So let me rewrite this as 10 over n minus 3 times n minus 1. What the cover-up method says is that, okay, if I'm going to take this first term, a over n minus 3, right? What makes the denominator 0? Well, n minus 3 is 0 when n is 3. In the original, I'm going to cover up the n minus 3 term and plug in the value 3. So if I cover up the n minus 3 term, I'll be left with 10 over n minus 1. Plug in 3, I get 10 over 2, which is 5. So this is 5 over n minus 3 plus, same thing I'm going to do with this second term. So it's b over n minus 1. What makes the denominator 0? Well, when n minus 1 is 0, n is 1. Now in the original, I'm going to cover up the n minus 1 factor, and then I'm going to say, okay, it's 10 over n minus 3, plug in 1, I get 10 over negative 2, which is negative 5 over n minus 1, which is the same thing as 5 over n minus 3 minus 5 over n minus 1. Alright, now the trick with this is to identify what the first couple of terms are until you see some constant cancellation. So at n is equal to 4, I'm going to have 5 minus 5 thirds plus 5 halves. This is when n is 5 minus 5 fourths plus 5 thirds. This is when n is 6 minus 5 over 5 plus 5 over when n is equal to 7. This is going to be plus 5 over 4 minus 5 over 6 dot dot dot. Okay, so what do we see? The 5 over 3's will cancel, 5 over 4's will cancel, 5 over 5's will cancel, dot dot dot. So what are we going to be left with? We're going to be left with 5 plus 5 halves. Now you could write the end statements if you want, but the trick to this is also noticing, okay, in this case, in these partial fractions, right, n is in the denominator, and there's only a constant in the numerator. When I plug in infinity, right, these are both going to go to 0. So technically I have plus 0 plus 0. So this becomes 15 over 2. That's how it's going to converge. So if you don't want to spend your time figuring out what those last 2 or 3 terms are going to be, you know it's going to be expressed in terms of n, and you're going to be taking the limit as n goes to infinity. So if it's 0, then you just have to take your first constant terms, and that's usually the case in these cases. Alright, the next test is the comparison test. There's 2 kinds, so I'm just going to split this right down in the middle over here. The first kind is the direct, and the second kind is the limit. Usually both of these will work in very similar manners. What does the direct comparison test say? Well, let's say if you have your original a at n, right? This is find some value b at n such that 0 is less than a at n, which is less than or equal to b at n. So essentially this value b at n is always going to be greater than a at n. If you find such a b at n, if b at n converges, then a at n will converge. So essentially, if the larger one converges, the smaller series will have to converge. However, keep in mind that if the larger one diverges, that does not mean that the smaller one diverges. It's actually the opposite in that case. You need to find a b at n such that 0 is less than b at n, which is less than or equal to a at n. So now your series has to be the bigger one. And then, if b at n diverges, a at n diverges. So that's the official test. Now, you might be thinking, well, how do you find b at n? There's millions of series out there that you're probably going to come across. So how exactly do you find b at n? Well, you know the most important ones. You know all the p series. You know the general geometric series, for example. So what can you do? Well, one of the things you can do is, let's say if I have a series n squared over n to the 4th plus 3, for example, right? N squared plus 1 over n to the 4th plus 3. Well, in this case, what you could do is you could figure out, or I guess that's a bad example. Let me try this. If you have n over the square root of n to the 6th, right? So I'll just erase this. If you have n over the square root of n to the 6th, I'm going to put a plus 1 here, for example. I'm going to put like a plus 3 here. And you're like, okay, well, I can't really evaluate this with any of the things that we know. What you can do is you can say, okay, as n goes to infinity, right? What are the dominating terms? On the top, I'm going to have an n, and I'm going to have on the bottom n to the 6th, right? Which is equal to n over n cubed. It's equal to 1 over n squared, right? In this case, it might be helpful to do a direct comparison with 1 over n squared. The thing is, and as soon as I go through the limit comparison test, it'll become apparent, is that oftentimes proving that 1 over n squared is larger than this can be difficult. And it can often require multiple steps as well. And so this is an example of a thing that could come if it's like intuitive, like if you can immediately see, okay, I need to use 1 over n squared or 1 over n cubed, but oftentimes the limit comparison test might be the easier one. So the limit comparison test says that given an a at n, find some b at n. Now this one doesn't necessarily have to have any restrictions. This one is just find b at n, and if the limit as n approaches infinity of a at n over b at n is equal to a constant L. So if it's not infinity or if it's not 0, it has to be finite. So L must be finite and positive in this case. And then A at n follows B at n. And so what this essentially means is that both converge or both diverge. Alright, so when can we use this? Well, if we look back to our earlier example, I'm not going to go through all of the work with this, but what you could do is, actually it might not be that bad. If my A at n is equal to n plus 3 over the square root of n to the 6 plus 1, I evaluated its behavior as n goes to infinity, and I found that it models 1 over n squared, and I know that 1 over n squared converges. So I'm going to let b at n is equal to 1 over n squared. So my limit as n goes to infinity becomes, or of a at n over b at n is equal to n cubed plus 3n squared over the square root of n to the 6th plus 1. And so what happens is that as n goes to infinity, the dominating terms become n cubed and the square root of n to the 6th, and this is just going to be 1. And so because the limit as n goes to infinity is equal to 1, and our L value is 1 in this case, it's both finite and positive, so that means that A at n converges. Why? Because B at n converges. If B at n diverged, if we found if our A at n had something related to 1 over n, and we use B at n equals 1 over n, and we found out that L is finite and positive, then A at n would diverge. So an example. Okay, this is very similar to the one, I did not mean to do that, but I can work through a similar example again. So if I have n minus 1 over the square root of n to the 6th plus 1, over time this will model 1 over n squared. How about we try and use the direct comparison test for this one? So what do we know? We know that it models 1 over n squared, right? So let's think about the inequalities that we can write. Plus 1. Well, we know that n minus 1 on the top will obviously make it smaller. So this is smaller than n over the square root of root n to the 6th plus 1, right? That's a fact. We also know that if this plus 1 got removed in the denominator, because then the denominator would become, So if we remove the 1 in the denominator, then this inequality is also true. Because we remove the 1 in the denominator, that means that the denominator becomes smaller, and so that means that the actual function n over the square root of n to the 6th is larger. And then we know that this is equal to 1 over n squared. And so because we know that this converges, we know that each of these will converge, and so this last one must also converge. And so this is an example of how you would use the direct comparison test for a thing like this. Just notice though that there was a lot more intuition involved in this one compared to the limit comparison test, where it's just crunching it out and working through and identifying it just at the very end what the limit would be. In this one, it's a lot more about, can you figure out the proper inequalities to set up in order to figure out how exactly this test will relate to a convergent or divergent series. Alright, so we're moving on to some of the last few ones. So the test I wanted to do this time was alternating series. So what is an alternating series? I say A dot S, the alternating series would be A dot S dot T, this abbreviation is common, and you can use it on the AP exam and you'd be fine. So what is this? Well, it has to be the sum, generally as n goes from 1 to infinity, of some value a at n, where a at n can be expressed as -1 to the nth times something else, or -1 to the n plus 1 times something else, depending on whether the even terms will alternate or whether the even terms will be negative or the odd terms will be negative. And so how do we prove that one of these is divergent? Well, there's two steps. So the first step is b at n must decrease. For large n. And so this is the same idea with the integral test, where oftentimes you take the derivative of b at n, so b prime at n, and then find out whether on the larger interval going up to infinity, whether it's always negative or primarily negative. Then because it's going to be decreasing, that's the fastest way to prove this first condition. And the second one is that the limit as n approaches infinity of b at n must be 0. Now what does this prove? This proves convergence. So if any one of these aren't satisfied, then it diverges. But what do you have to think about now? One of the things that you have to think about is, and this is a new concept that hasn't been introduced before, is the idea of absolute versus conditional convergence. So this test is really useful for identifying on like a multiple choice. If it says, does it converge or no? And if it's an alternating series, then you just have to use this. But if it's like a free response question that asks you to further develop the convergence level, then you have to think about what it means to be absolutely convergent. So what does this mean? This means that a at n converges by the alternating series test, and the absolute value of a at n converges by some other test. A lot of times you'll see b at n be something like 1 over n squared, something like that. So you can use p series, but any other test to prove that just the absolute value sequence, so think about the -1 to the n part being removed, if that converges, then it's absolutely convergent. Then there's also the second type, which is conditional convergence. So what does this mean? A at n will converge by the alternating series test, but the absolute value of a at n diverges by some test. And so that's the idea of conditional versus absolute convergence. In one of them, it converges depending on what test you use. In the other one, it's always going to converge regardless. And now the idea of remainder of alternating series is something that I'll cover in the last section. So for now, this is the general idea of the alternating series test. One of the things I will point out, this is kind of like, you can call it, I guess, like an important fact to know, is the idea of, you'll often see trig. And so you'll often see something like cos of n pi. Now, at first glance, you might think of maybe integrating this, or maybe trying to use some direct comparison. But the thing to recognize is that if you think about the cosine graph, right? The cosine graph model is something like this, where it's 1, then it's -1, then it's 1. And so this can be rewritten as -1 to the power of n, right? And so this is how you convert a trig. It has to be cos because sine will just alternate at 0, so it'll just be 0 always. But if you have a cos in the numerator or in the denominator, this is the conversion you have to make in order to convert it into an alternating series and then use the alternating series test. So let's give it a shot. for this, I see that I have an alternating series of the form -1 to the power of n plus 1 times some value b at n. And so I get my b at n is equal to n plus 1 over n cubed plus 1. Now, for the purpose right now, I'm not going to take the derivative and show, or I guess, no, we have time. It's okay. So b prime at n is equal to, now remember we're using quotient rule, so we take the derivative of the first function, which is 1 times n cubed plus 1 minus n plus 1 times 3n squared over n cubed plus 1 squared. So I have n cubed plus 1 minus 3n cubed minus 3n squared. This is negative 2n cubed minus 3n squared plus 1 over this n cubed plus 1 squared. So what do I know about this function? Well, I know that as n gets larger and larger, the denominator is always going to be positive. This numerator is going to be primarily governed by this negative 2n cubed. And so from n equals 3 onwards, n cubed is going to be always positive, but that the negative 2, right, suggests that it's going to be negative. You can also verify this by identifying that there's no actual zeros within this interval 3 to infinity. And so at any point, if there's a negative and there's no zeros, that means that the entire function will be negative in that interval. And so because the derivative is always negative, b at n is decreasing. So as you can see, this is probably the hardest part of the alternating series test, is proving that it's decreasing, because it's the one that takes the most time. That was part 1. Part 2, I take the limit as n goes to infinity of n plus 1 over n cubed plus 1, which is equal to 0, because the denominator will grow faster than the numerator. And so because these two conditions are met, I know that a at n is convergent. Now what about absolute convergence? Well, I'll just do it on the side over here. If I have n plus 1 over n cubed plus 1, what does this approximately model? It's approximately 1 over n squared, right? So I'm going to use the limit comparison test. So I'm going to take the limit as n goes to infinity of n plus 1 over n cubed plus 1 all over 1 over n squared, which is equal to the limit as n approaches infinity of n cubed plus 1 over n cubed plus 1. Sorry, this is plus n squared, which is equal to 1. And so because 1 is a finite and positive number, this the series n plus 1 over n cubed plus 1 will converge. And so a at n, the original thing, is convergent absolutely, because we tested it by the alternating series test, and then we also used the limit comparison test in order to ensure that the absolute value of the function, which is right here, is convergent as well. Okay, so this is the second last, and this is probably by far the most important one. So based on the tests that we've done so far, the most important ones are probably the nth term test for polynomials, because those come up in multiple choice a lot. Those are very quick. P series, I'm not going to specifically call it important. It's something you should just be able to recognize. The alternating series test will always come up. The test I'm about to do, the ratio test, will also always come up. And then the integral test is one nice to know if you ever see ln and geometric series. So some of them you should just know off the top of your hand. The ones you should focus on, like memorizing the formulas, are alternating series, ratio, and geometric. And then maybe the limit comparison if you feel like it'll help. Okay, so ratio test. So what is the ratio test? The ratio test says that given some a at n, I have to find the limit as n goes to infinity of the absolute value of a evaluated at n plus 1 divided by a evaluated at n. And then I can get three results. If I have less than 1, it's convergent. If I have equals 1, it's inconclusive. If I have it greater than 1, it's divergent. So for this test and then the final test, the next one, you'll see that it's all about 1. Equals 1 is inconclusive, less than 1 is convergent, greater than 1 is divergent. And so why is this useful? Well, this is almost always one of the only ways that you can do anything with a factorial. Why? Well, let's say if I have n plus 1 factorial, and I'm dividing by n factorial. Well, n factorial would be the original. How am I supposed to use any of these tests? It's not a geometric series. You can't integrate factorial with elementary functions. You can't really use the limit because factorials don't follow polynomial growth. So the ratio test allows you to cancel stuff out because n plus 1 factorial is just n plus 1 times n factorial. So this overall expression is the value is n plus 1, so the factorials are just gone. So whenever you see a factorial, always turn towards the ratio test. Also for the stuff in the next video where we'll talk about Taylor series and intervals of convergence and radius, the ratio test is one of two methods that can be used. One of the two only methods. The other one is the next test I'll be covering, the root test. So let's try an example. As you can see, this one has a factorial, so I immediately know I need to use the ratio test. So it says I take the limit as n goes to infinity of e to the 4 times n plus 1 over, sorry, I forgot the absolute value, n minus n plus 1 now, plus 1 minus 2 factorial, times, because I'm dividing, I'm just going to multiply by the reciprocal. So I'm going to multiply by n minus 2 factorial over e to the 4n. Alright, wherever there's an n in this first term, I substituted n plus 1, and now it's just a matter of simplifying and identifying the limit. So, e to the 4n plus 4 in this case, because when I distribute the 4n, divided by e to the 4n. That will just get me e to the 4. Now, n minus 2 factorial over this is n minus 1 factorial. Well, this bottom part, remember each time we're subtracting 1, so this is n minus 1 times n minus 2 factorial. Oops. And so I get over n minus 1. And so when we evaluate the limit as n approaches infinity, this is 0. And because 0 is less than 1, it's convergent. So that was an example of using the ratio test. Now the final one is the root test. So what does the root test say? Well, the root test says that if you have a function, and usually you use this if you have n in the power, because sometimes it might not work very well with the ratio test if you have n in the power. If you take the limit as n goes to infinity of the absolute value of a at n raised to the power of 1 over n. And then the same principles apply. You'll get some value L. If it's less than 1, there's convergence. If it's equal to 1, it's inconclusive. If it's greater than 1, it's divergent. Okay, one of the important things to consider here is if I have the limit as n goes to infinity, as n goes to infinity of n to the power of 1 over n. Now this may seem a little odd. It's infinity to the power of 0. This is not indeterminate though. This is actually 1. Or at least for this particular definition, n to the power of 1 over n is evaluated as 1. So this will be essential when we use the root test for some of our examples. So for example, in this one, I see a ton of powers, and I know I'm not going to be able to do the ratio test and get good numbers because I have an n in the denominator and in the numerator. So I'm going to use the root test. So I'm going to take the limit as n goes to infinity of the absolute value of n 4 to the 2n to the power of 1 over n. Alright? And then when I distribute this 1 over n to the top and the bottom, I get the following. I get the limit as n approaches infinity of n to the power of 1 over n minus 3 over 4 squared. Right? Because in the top, I multiply the power by 1 over n, so I get 1 over n minus 3. And so this is equal to, well, this is the limit as n approaches infinity of n to the power of 1 over n. Because of this subtraction, I'm going to say divided by n cubed, and then all divided by 16, which is equal to the limit as n approaches infinity of n to the power of 1 over n over 16 n cubed. Now this top part will evaluate to 1, but because the bottom is 16 times infinity cubed, this is equal to 0. So because 0 is less than 1, this will converge by the root test. Okay, and so the final topic I wanted to talk about was series estimations. Now, a lot of times you use partial sums in order to estimate a series. And so we denote partial sums by s at n. Some common partial sums include for a geometric series, it's a times 1 minus r to the n over 1 minus r. For something as simple as the sum of n, the partial sum is denoted by n times n plus 1 over 2. If you have n squared, for example, becomes n plus 1, 2n plus 1 over 6. Sorry, I think that's n cubed. And so these partial sums can be used to approximate the infinite sum, except what you have to consider is that there's a remainder. And so the general formula is that the remainder at any given point, the absolute value, is equal to the absolute value of the total sum minus the partial sum, which makes sense. I mean, if you have a partial sum and your sum amount off from the actual sum, that's your error. So remainder is often called error. And so the main one that AP wants you to know, the main error formula, is for an alternating series. That's that the remainder has to be, it's equal to s times s minus n, which has to be less than or equal to b evaluated at n plus 1. Or sorry, I'm going to stick to convention and I'm going to use a. So a evaluated at n plus 1. So that's the main remainder. However, so this is absolute value, I believe. However, this can be applied to other functions, non-alternating series functions. Sometimes this is a method that AP doesn't require you to know, but if you want to do a fast calculation, if you have time and you want to be more accurate, this is one that you can use. It's the following. Sn plus the integral from n plus 1 to infinity So the lower bound is the partial sum plus this integral it has to be less than or equal to the actual sum, and the sum has to be less than or equal to that same partial sum plus the integral from n to infinity of this. Now once again, this is optional to know, this isn't required for the AP exam, but a lot of times when you have stuff that you've used the integral test on, such as lawn functions or reciprocal functions, this specific one might be more accurate than the alternating series remainder. But overall, just to do a recap, what we did was we initially talked about sequences and series, their definition, some of their small properties, and then we went over the 9, technically 10 convergence tests, and then we did an example for each. I really hope that this video helped you in understanding the basic part of series, especially the convergence test, because oftentimes students can get bogged down on the AP exam in terms of multiple choice on what to use, when to use it, and exactly how it works, especially things such as like function has to be decreasing. So I hope that this video really helped you with that. Remember to like the video if you benefited from it, and comment down any new content or any suggestions you have. And remember to subscribe to my channel, Patel Academy, and hit that notification bell so that you can figure out when my next video on series or on any other topic, calculus, physics, anything, is uploaded. Thank you so much, and I'll see you guys in the next video.